Hello, my name is Kaya Mitchell, and today I'll be presenting my Physics 1 lab. Introduction. The purpose of this lab is to observe an object moving at constant velocity, or uniform motion, and apply Newton's second law, or the momentum principle, to explain the motion that occurs in a recorded video. By completion of this lab, I strengthened my rudimentary understanding of the momentum principle by not only analyzing the uniform motion of an object in an experimental setup, but by also representing this measured motion with a computational model, which required me to address Newton's second law at face value. To carry out such experiments, I first used an application tracker to capture and analyze a video of a cylinder container rolling across the table in constant motion. After collecting the proper data from the experimental setup itself, I then constructed a computational model using Glowstrip to articulate the motion of the container observed in the video. And finally, I analyzed and compared the two data sets in Google Sheets. So I recorded an object moving in uniform motion and collected the necessary initial conditions that would be needed to predict the object's new position and velocity, according to momentum principle. When collecting this data, the origin was placed at the center of mass of the object so that the x-axis was pointing in the positive x direction. Observations of the container in constant motion were translated into Glowstrip by first editing the code to include the necessary initial conditions to predict the object's new position and velocity according to the momentum principle. In this case, we needed the start and end time of the container's motion, which was plugged into the code right here, where t equals 0.033 and delta t was also 0.033, which marks the time step of each frame. And for the while loop, I set t less than 0.968 because this is the last time that was recorded on my experimental data. The container's position vector was indicated by the point mass of the first frame of the video, and the measurements were calibrated to the length of the container, which was 0.24 meters. To estimate the initial velocity, I used two positions and two time steps and plugged these values into the equation. Velocity equals change of position divided by change in time, which gave me the initial velocity of 1.06 meters in the positive x direction. I then plugged this value into the x-coordinate of the velocity vector in Glowscript. Under the while loop, I then set the net force equal to 0 in order to agree with Newton's first law. According to momentum principle, with no net force being applied to the system, the object will move in the same direction with the same speed, thus modeling a system with constant velocity. I then used the momentum principle to update both the velocity and the position of the object, and I translated the following equations into the equations for Glowscript, where the final velocity of the ball was calculated by adding the initial velocity to the net force times change in time. And from here, you then found the final position by adding the initial position to the ball to the average velocity times change in time. But in this case, we just use the final velocity. Upon reviewing the data collected from both the experimental setup and computational model of the container's motion, we see that the velocity of the computational model is perfectly linear as expected. Although the observed motion was quite different from the computational model, being that the model does not account for friction and air resistance, I would still say that overall the computational model did a good job of modeling an object moving in constant motion. With the simplifying assumption that there was a net force of 0 acting on the object, we were able to predict the object's future position and velocity using the momentum principle, while neglecting air resistance and friction. If we were to change the orientation of the axis and tracker, the direction of velocity will change, however the magnitude will remain the same. If we were to flip the x-axis and make it negative, the position will progress negatively, therefore giving us a negative slope for velocity. Thus, with a flipped axis, the direction vector will change. However, the relationship between the object's location relative to the axis as it moves through time will not change as long as the object is moving with constant velocity. For an object moving at constant velocity, there must be an equal amount of pushes and pulls acting on the object. However, we do not know the total amount of opposing forces that are acting on this object. Though we do know the opposing forces are equal and opposite in direction, thus canceling each other out. So by setting the force equal to 0 in the computational model, we do not know how many total pushes and pulls are acting on the system, but we do know that these forces are equal in magnitude and opposite direction, thus canceling each other out and giving us a force vector of 0. Thank you for learning physics with me, and I look forward to seeing you next time. Bye!